Okay, so we've got a Suvat equation again. We've got a particle, so we know that we can ignore air resistance and we can ignore any rotational motion. We've got constant deceleration of 2.5 meters per second squared, and we know that there's movement in the positive direction of x, and we've got a speed of 15 meters per second once it's past that origin O. So starting off with our diagram, we know that we've got movement in the positive x direction. I know my deceleration is going to be acting opposite to that, so that's 2.5 meters per second squared. The 15 meters per second, if we read back before that, that's when it passes the origin O. So I'm going to mark on the origin O, and then I can draw my arrow saying it's moving this direction with a velocity of 15 ms to the minus 1. Okay, now thinking about this, it's starting off moving in the positive x direction, so my particle is going to start going this way, but as it's decelerating, eventually that's going to decelerate down to 0, so it's going to instantaneously stop, and then it's going to take a path back in the opposite direction. So that dotted line there is just going to show the expected path of my particle. Obviously not with the big curve, but that's just to represent where it's going forwards and backwards. Right, marking on positive direction makes sense to put it in the same direction as the positive x-axis. Looking at the data, we know nothing about the displacement or any distances. We do know that the initial velocity is 15 meters per second. We don't know anything about the final velocity at any particular point, apart from we do know that at the instant when it changes direction, that's going to be a speed of 0 meters per second. So that might be something we're going to use later. The acceleration is going opposite to my positive, so we've got 2 minus 2.5 meters per second squared. And time is not something that we're given either. So at the moment, we've only got 2 pieces of data. So it looks as if we are going to have to use that specific point where v is equal to 0. First of all, we're asked to find the time between the instant when P first passes through O and the instant when it returns to O. So in this case, we're not thinking about distance with Suvat, we're thinking about displacement. So by the time it's returned back to the origin, it hasn't actually changed position, therefore its displacement is 0. So for this part of the question, we can treat S as being equal to 0. So now we've got S, U and A. We're selecting our formula, and we're trying to find T. So we're looking for one with S, U, A and T, which is going to be S equals UT plus a half AT squared. Right, so we know that our displacement is 0. We've got 15T plus a half times minus 2.5 T squared. Now looking at this, I've got one variable. However, I have got a variable in T squared. So I'm expecting to be solving a quadratic here. So I'm going to do a bit of rearranging, and I'm going to bring my T squared to be positive. So I'm going to have 1.25 T squared, and I'm going to bring the 15T across as well, and that's still going to be equal to 0. Now, if it wasn't equal to 0 on that side, and we did have a coefficient of units, then we would think about using the quadratic formula, whereas in this case, we can simplify matters by factorising with t. So we've got 1.25t minus 15 being equal to 0. And there's 2 possible solutions here. Either that this original t, which it might help you to consider is inside its own bracket, could be equal to 0, or our alternative solution here, t could be equal to 15 over 1.25. And using our calculator, which we're able to do, we can say that that is equal to 12 seconds. So it does ask us for the time between the instant when it first passes through T and the instant when it returns to O. So therefore we've got to think about the difference in time between those two. So we're going to do 12 subtract 0. So my final written answer for part A is going to be the total time is 12 seconds. Right, on to part B. We're now looking at the total distance travelled by P in this time. Now, we're given the time now, so that's now an extra piece of information which we could use if we wanted to. However, because the displacement there is 0, we're going to have to be a little bit more savvy about this because it wants the total distance, so it's looking for our journey out and back. So what we might want to consider is breaking it into two parts, going from O to its maximum point, which we could give a letter here of M, and then from M to O, which we know is going to be the same distance. So we might want to reconsider Suvat here. So this time, S is what we're trying to find out. We still know that the initial velocity is going to be 15, but this time we can say that V is equal to 0 for the halfway point. Okay, so V is equal to 0 at M. So now we've got three bits of data. We've got U, V and A, and we're going to find the displacement from O to M. So that's going to be S. So we're going to use V squared equals U squared plus 2AS. Subbing in our values, so V at that point M is 0 equals 15 squared plus 2 times minus 2.5 times our displacement S. Okay, so we're going to use our calculator. We're going to do a bit of rearranging. So we've got 5S equals 225, and therefore S has got to be equal to 45 metres. So that's our displacement from O to M. So therefore, my total distance is going to be twice that. So my total distance is going to be equal to 90 metres, going from O to M and then back from M to O.